Well, greetings, folk. It's great to be talking to you again. Today I'm going to be delivering to you part 2 of the story of the Comet-1 accidents. And just a beautiful aeroplane. I just was talking with Ian there a moment ago about how beautiful this aeroplane is. The purity of line, it's just unsurpassed. So today we'll be talking about the in-flight breakups. And I think that for anybody who has even a vague association with aviation and who's heard of the Comet, if you ask them what caused these accidents, they're going to say, oh, it was the square windows. Now, I first heard about these Comet accidents when I was in my early 20s. And I really just wondered, because de Havilland had been making aeroplanes for a long time. They had a great reputation, and it just seemed a very odd thing that you put square windows on an aeroplane and they fail or cause the failure. It just sounded like what I'd call a rookie error. So anyway, let's have a look and see. So this here is a shot of a square window, or part thereof. Now, the windows are actually a bit more rectangular, but by calling them square, we use a bit less oxygen, so that's probably an advantage. But also, they're not perfectly square in the sense that they have radiused corners. Now, the corner radius for the cabin windows on the Comet was 75 millimetres, and they used a 100 millimetre radius for the other cutouts, like the ADF aerials on the roof. So it wasn't like a square with a square corner as such. Now, the puzzling thing to me is that, okay, if you want to blame the square windows of the Comet for the in-flight breakups, what other evidence is there or was there of pressurised aircraft with square windows that didn't have problems? Well, the reality is you don't have to look very far for that. I mean, the Douglas DC-6 for one, very popular aircraft, over 700 delivered. The Canadair North Star at the bottom left there, that was a pressurised version of the Douglas DC-4, built under licence in Canada and using Merlin engines and square windows. No structural failures. Now, this was, which was also called the Argonaut in England, was about 70 knots faster than a DC-4, but unfortunately it was also shatteringly noisy for the occupants, so a bit of a mixed blessing there. And when BOAC was running their Comets to Tokyo and back, it was an 86-hour one-way trip, so I think you would have been able to claim for hearing loss after that. But on the top right here we've got the wonderful and imposing Boeing Strata Cruiser. This particular one was one of many delivered to Northwest Airlines, or Northwest Orient as they were called then. And Northwest was one of the airlines that specified square windows for the main cabin and the lower cabin as well. Now, Northwest didn't keep all of their aircraft for full life. They had a couple of accidents unrelated to structural failure, but most of their aircraft were scrapped finally at a life of 31,000 hours and no structural failures. So you've really got to say to yourself, well, how can it possibly have just been the square windows? So moving on to the Comet in-flight breakups, there were 3 of them. The first one was an aircraft that departed Calcutta. As you can see, that was in May of 53. But the other 2 that occurred in 54 are of more interest to us today for reasons that will become apparent. So the Calcutta aircraft was climbing on departure for Delhi, and it entered a monsoonal thunderstorm, and for an unknown combination of reasons it broke up. But there was no evidence that the fuselage had structurally failed other than through overstress, either from the turbulence of the storm or from perhaps the pilot over-manipulating the powered controls to try to escape. Now, to the great relief of de Havilland and the British government, this accident was little publicised because, of course, they were very concerned to protect the image of the comet at this time. So not much was heard about that, but nonetheless it wasn't really significant in the context of the later two accidents. So the two that occurred in 1954, we had the first one to Yoke Peter. Now I'm going to name these aircraft using the phonetic alphabet of the day. So we're going to meet Yoke Peter for a start, and then we're going to meet Yoke Roger in a few minutes, and eventually Yoke Uncle. So it was kind of like the Yoke family, it seems. And it all got to be a bit Monty Python, so it's little wonder to me that eventually the phonetic alphabet was changed. So in January of 54, Yoke Peter was lost on departure from Rome, heading toward London, and it broke up and crashed into the sea south of the island of Elba. And then in early April, Yoke, departing also from Rome, heading to Cairo, was lost into the Tyrrhenian Sea off Naples. So Yoke Peter on the 10th of January 54, we know, even in the days before flight recorders and cockpit voice recorders, we know that something happened suddenly and catastrophically to this aeroplane, because Captain Alan Gibson, Distinguished Flying Cross, who was the captain of Yoke Peter, was in contact with the captain of a BOAC Argonaut, Howard Jigg, HJ. And Captain Gibson was saying, "George Howard Jigg from George Yoke Peter, did you get my?" And that was a sentence that was never finished. So witnesses reported flaming debris falling out of the clouds into the sea. And that aircraft had only done 1,290 flights, which is a very small number really. So of course, once this accident happened, particularly as the cause of it was unknown for some time after that, a lot of the operators voluntarily grounded their Comets. Fortunately, the wreckage of Yoke Peter was only at a shallow depth, mainly at a depth of about 100 metres. So in the end, they were able to recover 70% of that and piece it together in Farnborough. And in the best British tradition, a committee was created under Charles Abell to investigate the causes. Now, bearing in mind that it is said that a camel is a horse designed by a committee, we have to then consider what this committee actually did. Now, they didn't really know what this might have been, so they kind of took a scattergun approach, it seems to me, and they looked at quite a number of things. But in the end, they felt that either an engine fire or perhaps an uncontained failure of the engine was the most likely cause. And structural failure of the fuselage wasn't considered. Now, I can imagine that the voice of de Havilland was to be heard over Charles Abell's shoulder, because de Havilland had done a vast amount of work to prepare for the Comet, as we'll see, and they were very confident that there wouldn't be a structural failure of the fuselage. But nonetheless, 39 days later, the Abell Committee released its report. Now, how in heaven's name you can look at all of these possible causes, investigate them and report on them in 39 days is a bit curious. And Abell's committee found no fault with the design or construction of the Comet. But it's got to be said that this was hardly an independent inquiry, because Charles Abell was a senior operations executive of BOAC. Now, BOAC, backed by the British government, was desperate to get the Comet back into service. So it was hardly really an independent process. Now, while the committee was cogitating, de Havilland decided that they'd go and make a number of modifications themselves. And in particular, they fitted steel containment rings around the turbines of the Ghost engines. So if you have a look at the Ghost cutaway there, on the left end of the main, the one and only shaft, which by the way was rotating at 10,250 RPM at takeoff, but on the left end you've got that centrifugal compressor that looks as though it came off a steam engine. So that was hardly likely to fly apart even at those RPM. But down at the other end of the shaft, you've got that single stage turbine. Now that was bolted to the end of the shaft, so de Havilland thought, well, perhaps that came off, or perhaps there was an uncontained failure of the turbine disc, so they put the containment rings around the turbines to cover that possibility. So the British government, BOAC, and I'm sure de Havilland as well, were very keen to get the Comets back into service, so they vetoed any more detailed investigation. And on the 23rd of March 54, revenue services resumed. Now there was a lot of disquiet about this, as you can imagine, because here we are, the world's premier aircraft at the time had suffered a catastrophic loss whose causes had not been determined. So Lord Brabazon, the head of the Air Registration Board, 12 days after the Comet services resumed, he felt obliged to give a statement of reassurance. And I've emphasised the first sentence there, although no definite reason for the accident has been established, because really that puts everything else into context. But nonetheless, the august Lord Brabazon's words were apparently spread like a healing balm over the waters of disquiet, and things carried on. But unfortunately, 4 days later, he was going to have to choke on his words because the Naples accident occurred. Now this was Yoke this time in early April. Very similar to the Elba accident. This aircraft, though, had only done 900 flights, so only 900 pressurisation cycles. It was at 1,000 metres depth, so there was no possibility of recovering wreckage from that depth. So only the odd bit of floating wreckage plus the bodies of the victims were able to be recovered. The certificate of airworthiness was withdrawn, and a proper investigation this time was launched. So the first thing, of course, is the investigation is going to consider what could possibly have caused this. I mean, they were both sudden events with no mayday calls made. Other possible causes were ruled out. So it really came down to explosive decompression of the pressure cabin as being the only possible cause, the only possible primary cause. And the forensic examination of the bodies of the victims confirmed that explosive decompression had occurred. And this was the first time that forensic examination of the passengers or crew killed in an accident, an airline accident, had been used as a factor in determining what the cause was. So again, if we look at explosive decompression, there's not that many things that can cause it. And a number of them were considered in relation to fuselage overstress. But really they were pretty quickly ruled out, and it only left us with two possibilities. One was that there was a weakness in the design of the Comet cabin somewhere, leading to failure in normal loading, or alternatively, that there had been a fatigue failure of the cabin. Now, de Havilland knew a little bit about fatigue because in 1951 they lost a de Havilland Dove in Australia just near Kalgoorlie when one of the wings came off due to fatigue of the spar. So fatigue wasn't an unknown quantity to them. So these were the two things that the investigation set out to look at. And just for the record, a definition of metal fatigue, which I'll allow you to read, I don't need to read that out. But nonetheless, you don't need a whole lot of stress to cause it in a kind of metal that may be susceptible to it. And as we'll see, unfortunately, the aluminium alloy used in the Comet fuselage was susceptible to fatigue. So just before we get into detail there, I want to show you an incident that befell Yoke Roger another member of the Yoke family, in 1953 when it was taxiing for a night takeoff from Calcutta. Now I'll give you a clue. The aircraft ran off the taxiway. Now, would anybody care to hazard a guess as to what might have happened here? Well, that's really good, because I wouldn't have been able to either. Now, a night takeoff, in those days, night operation of airliners was by no means universal, because a lot of the ground facilities just weren't up to it. And at Calcutta, the taxiway lights were extremely dim. So the captain, who was flying the aircraft from the left seat, or taxiing it in this case, he had to use the landing lights of the aircraft to illuminate the taxiway. Now, that little inset there shows the nose wheel, steering wheel on the captain's yoke. So he was manipulating that. But with the early Comets, you couldn't just turn the landing lights on the ground, because they'd overheat and the filaments would burn out, and then you'd be left in the dark. So what you actually had to do was alternate the landing lights as you were taxiing, because you could only leave either one of them on for a short time. So the panel controlling that was way down on the left wall of the cockpit to the captain's left side. So this aircraft was going around a bend on the taxiway. The captain turned hard to his left to reach the landing light switch to change from one to the other. He accidentally let go of the nose wheel steering wheel. The nose wheel steering centred, and the aircraft ran into the mud on the side of the taxiway. Now, okay, these things happen, and you might say, well, you know, that ought to be recoverable. But rather than expose himself to the embarrassment and the odium of having a bogged aircraft, having to unload all the passengers, what he did, he thought, I'll just gun the starboard engines and I'll blast my way out of this. Well, what he blasted his way into was the starboard main landing gear just being ripped off. So in the end, it didn't turn out too well for him. So that was the story of Yoke Roger. They did actually repair it. Now, one fact that becomes relevant here, and I'll explain why in a moment, is that the Comet had to fly very high in order to get good fuel consumption, because these early turbojet engines just used a hell of a lot of fuel at low altitude. And taking it from the pilot's notes, at 30,000 feet, the Comet was using half as much fuel again, and that's pounds of fuel per air nautical mile, as it was at 42,000. So there was a very strong incentive there to get good range from the Comet to fly high. And in fact, in the pilot's notes, you'll see the curves for 42,000 feet. But if you fly that high, you can't just let the poor passengers gasp and die due to lack of oxygen. So you've got to do something about it. And typically you want to keep the pressure, the so-called cabin altitude, to about 8,000 feet, so the punters don't have any discomfort. Now, I'm not going to go through the numbers, they're all down here and they'll be on the video, but what it meant was that in order to get an 8,000 foot cabin at a 40,000 foot cruising altitude, the Comet cabin had to be pumped up to 8.25 psi. Now, by comparison, a Douglas DC-6 cruising at, say, 25,000 feet only needed a cabin pressure of 5.5 psi to do that. So the Comet's cabin pressure was half as much again as that of the DC-6. And that was certainly a factor in some of the things that happened. Now, when I was preparing this, I was thinking about the Comet and feeling rather sorry for it, really. So here's my rendering of it at 42,000 feet, hurtling along in the near stratosphere, with the cabin pumped up to 8.25 psi, and the Comet rather feeling the pressure, let us say. So this time, they did a proper investigation. they tasked the Royal Aircraft Establishment at Farnborough, which was the government instrumentality that advised the government and others on aviation technical matters. It took them 5 months to do this. They put Yoke Uncle into a test tank, and we'll see that in a moment. And then once that inquiry was completed in September, Lord Cohen, a London judge, was tasked to head a court of inquiry just to seal the whole thing up. So why do you think to test the pressure of a cabin, you might do it in a water tank rather than just sitting on the tarmac? Because, I mean, this tank here had 900,000 litres of water in it, and a lot of work was required to do that. But why do you think you might do it that way rather than just blow it up or inflate it, let's say, on the tarmac?
So you can do more the delta pressure.
Say again?
To do with the delta pressure.
Yeah, that's right. It would blow into 1,000 pieces. So if you do it in a water tank, you don't have that problem. And what they were able to do was simulate a 2-hour flight, typical flight length for the Comet, in 5 minutes, pump it up to 8.25 psi, and then after only a short number of flights, the fuselage ruptured.
The most intensive probes into the Comet disasters have been carried out at the Royal Aircraft Establishment at Farnborough. One of them involved the testing to destruction of a Comet, seen here being placed in a special water tank with airbag seals at the points where the wings project on either side. The tank holds 200,000 gallons of water. After it had been filled, jacks beneath the wings caused a series of bumps as if in flight, and internal pressure was raised in the fuselage. After the equivalent of 5,000 3-hour flights, metal fatigue resulted in cracks and breaks. Information obtained from many scientific tests will, it's believed, lead to new Comet triumphs in the future.
Going into a little bit more detail here, it was actually 3,060 pressurisation cycles in this aeroplane failed, and it failed at a defect due to fatigue. So here's a shot of the Yoke Uncle point of fatigue with a little arrow there showing the actual origin point. And there are two things about this. This is a forward escape hatch on the left side. There are two things about this that stick out to me. What do you think they might be? Say again?
Square window.
Yes, square window. There are three things that stick out then. Okay. So, any thoughts?
The fuselage is actually ripped over quite a distance.
Yes, that's true. So look, the things that I noticed was that first of all, I mean, I know people were thin back in the 50s, but that's an escape hatch. And I wonder how many adult passengers these days would be able to slide out through that. But the other thing noticeable to me is the very light weight of the stringers and the ribs in the fuselage. And you might have noticed that towards the end of the video as well. For a pressurised aircraft, these structural members just seem to be incredibly light and weak. So mid-1954 was a busy time for the Comet. Eventually, Yoke Peter, they recovered, as I said, 70% of the wreckage, and they took it all back to Farnborough and put it on a frame or an armature and reconstructed it. So let's see what this wreckage was telling us. Now, the tail section was recovered on the 26th of May 54, and I don't know whether you can read that there, but what it is, that's a piece of fuselage floor carpet embedded in the leading edge of the tail. So that tells you, first of all, that the tail was in place when the breakup occurred, and secondly, that the fuselage ruptured in a very violent way and ejected things like bits of carpet that then got stuck in the tail. So things were coming together here. Eventually, the top section of the roof containing the ADF aerials was recovered, and that was deemed to be the origin point of the failure, and that's the bit there on the right. And that's a close-up of part of the failed area. And there are two things that really concern me about this. Number one is the nature of the riveting, which I'll come back to. And the other one is how painfully thin that skin is. And I'll also come back to that. So the failure in Yoke Peter originated at a bolt hole, which is the one arrowed there. That was about 90 millimetres away from the corner. And there were signs of fatigue on either side of that. So what happens is once you get a rupture with the pressure inside the cabin, that rupture extends very rapidly. And what happened here, I'll just go back a moment, the fuselage ruptured back along the crown, and that flap of skin that you can see on the left side of the aircraft there, that actually was flung down onto the top of the left wing, where it left blue and white paint marks. So when you put it all together, it became very clear what had happened here, although not necessarily why. But nonetheless, the Royal Aircraft Establishment, who took a close look at this, they concluded that the failure of Yoke Peter, at least, and almost certainly that of Yoke off Naples, was due to fatigue failure of the pressure cabin. And in fact, as I say, it wasn't the 5,000 flights in the video, it was only 3,060. So then Lord Cohen started his inquiry, and he sat for 104 days. So he accepted the findings of the Royal Aircraft Establishment investigation, and by an amazing feat of gymnastics, he managed not to blame anyone for anything that had gone wrong, and I commend him for that, although for many other reasons as well. And so we have here fatigue failure of the pressure cabin. Now, there was writing on the wall here when it came to how flimsy the Comet was. And these references here from a gent called Chris Beaumont. He was the chief pilot for de Havilland engines. And one day he was on a Comet flight. He was standing in the cockpit doorway as John Wilson, the de Havilland pilot, flew the aircraft. And as they pulled a bit over 2.5 G in a turn, the fuselage floor buckled up underneath Chris. And the other thing was, they demonstrated the Comet prototype at the Farnborough Air Show only 3 weeks after it had first flown. That's pretty gutsy as well. But the pilots knew, without looking at the airspeed indicator, when they'd reached 340 knots, because the fuselage panel at the front buckled in, and you'd hear it like when you concertina an oil can, so they call it panting. And so if this is me in this aircraft, I'm going to be looking for the parachutes and the emergency exit, I think. So, and that's in page 39 of Empire in the Sky by James Hamilton Patterson, the paperback version, and an excellent book to read. So as I said earlier, was this just a rookie error on de Havilland's part? I mean, it's very easy to say, well, you know, they shouldn't have made the windows square and then none of this kerfuffle would have occurred. Well, the reality is they did a vast amount of research in preparation to build the Comet. As we'll see, they designed it to higher standards than were required. They checked the fuselage for fatigue, and really they did all and more that could reasonably be expected at that time. So the standards in 1949 weren't particularly stringent because they were mainly intended for non-pressurised aircraft. So as you can see here, they did quite a bit more. They tested the Comet to higher standards than was required, and they tested it over 2,000 pressurisation cycles again. But I've highlighted the 2P there because that was a cause of major problems. By the early 1950s, the standards for certification were really creeping up, and in particular there was an increasing understanding of the effects of fatigue and the potential risks. So by 1953, people were recommending that aircraft should be tested for 15,000 cycles before they could be certified. So de Havilland took their original prototype and they did 16,000 more pressurisation cycles in it before it failed, for a total of 18,000. So they were very confident, as I said earlier, that this was not going to be a problem to them, because the aircraft was only designed for a life of 10,000 cycles. But if we look at the Naples aircraft, that failed at 900 flights, so only 1/20th of the life that de Havilland had tested the aircraft to. So there's clearly a significant disconnect there. But in the light of recent knowledge, Professor Paul Withy of the University of Birmingham in 2012, he took another look at the expected fatigue life of the Yoke Peter fuselage, and he came up with a number of 1,272, which is only fractionally below the life at which it failed. So what de Havilland did wrong here was they retested the original fuselage, and for reasons that will become apparent in a moment, because they took the fuselage up to twice the pressurisation pressure 30 times, this had actually led to permanent stretching of the aluminium in the most highly stressed areas. And this is called cold working, which wasn't that well understood at the time. But that stretching relieves the stresses in that area and greatly increases the fatigue life. So now, as we kind of move to a close today, if we look at the causes of this accident, the first one, and I think really de Havilland needs to be hammered for this, they grossly underestimated the stresses at the corners of the cutouts like the windows. And in fact, when the RAE did their investigation and looked at this using the strain gauge technique, they found the actual stresses there were half as much again as de Havilland thought. Now, if de Havilland had known that at the time, and the strain gauge technique was developed in 1938, so it had been around for 10 years by the time de Havilland came to design the Comet. If they'd used that technique, they would have known immediately how high the stresses were at the corners of the cutouts, and they could have done something about it. So that was not their finest moment, let's say. So looking a little further here, okay, the Comet was on the cutting edge of technology, and we can forgive a certain amount for that. As I said in my earlier presentation, it was underpowered, and they were already concerned about the risk of fatigue in the wings, so they made them pretty robust, but that left the option, unfortunately, or the requirement to have quite a lightweight fuselage in order to maintain the payload. And bearing in mind the Comet was only designed for 24 people, and then before it got off the drawing board, that was increased to 36 and to 44 in the end. And also, as I mentioned, the high cruise altitude put a vast amount of stress on the fuselage compared to other aircraft of the day. So, the Comet fuselage used very thin skins. Now, 0.7 of a millimetre is 7 sheets of copy paper. That's all it is. 7 sheets of 80 gram per square metre copy paper that you'd use in your home printer. Now, the skins around the windows were a little bit thicker, but RAE at Farnborough, they were very concerned during the design phase about how thin these skins were. And this alloy that de Havilland used, I don't believe was used again, because it was found to be prone to fatigue. So not something that you want either. Now, originally, de Havilland was going to use Redux bonding around the windows, and I'll have a look at that in a moment. They had experience of that with the de Havilland Dove fuselage and also the de Havilland Hornet, but they decided that it was too hard, because this stuff, it's a kind of glue, and you've got to heat it to about 140 Celsius and then hold it under high pressure while it cures. So they said, well, to hell with this, we're just going to rivet the windows because it's too hard to use the Redux. So the riveting technique they used was called punch riveting. Now, the problem with punch riveting is that the rivet itself makes the hole. It's not like you drill a hole and countersink it, put the rivet in and then dolly it or whatever and clinch it up tight. The punch rivet punches the hole, puts the rivet in and does the whole thing in one hit. But it leaves a lot of compressive stresses around the edge of that rivet hole, which then actually caused cracks during manufacture. And we'll see one of those in a moment. But I mean, to me, is if I were an aeronautical engineer working on the Comet, and I look and I see cracks being caused by riveting, I'm going to say, well, you know, gee, this is fairly serious stuff we're dealing with here. Thin skins, countersunk holes don't really go too well. So let's have a look at this redux bonding. This is a section of Comet fuselage with the stringer redux bonded. And had they used redux bonding around the cutouts, the windows, etc., I don't think these accidents would have occurred, or certainly not when they did, because gluing them in place means that you have a very even distribution of stress rather than the stress concentrations that they ended up with. But in the end, they didn't do it, and history is history. So, what are they going to do to deal with these cracks? Let's have a look here. Well, there's a crack caused during the riveting process. This has obviously been de-riveted now. So they put a 1.6mm diamond drill stop hole in to stop the crack, but this particular crack kept growing, so it wasn't really a very effective technique. And in fact, Lord Cohen in his report said, you know, what in heaven's name are you doing using stop drilling to stop cracks in a highly stressed area? It's just highly inappropriate. These cracks were also under, in the case of Yoke Peter, they were under a doubler plate and under several coats of paint. And at the time, it was simply not possible to find cracks in that situation because the only available means of inspection were visual. So this hastened the thought, the use of X-ray among other techniques. So I'm going to leave you with a question today. Was it really the square windows after all? So thank you very much.